All right, so this video lesson is about kinetic theory, which is all about how atoms and molecules move around, and a little bit about energy as heat. So let's first talk about kinetic theory. We wrote down a definition in class, but here's another way to think about it. Basically, the theory states that all atoms and molecules that are in the universe are moving around. They're moving in some way, shape, or form. The faster a group of molecules are, the warmer its temperature would be if you could take its temperature. And the slower a group of molecules are, the colder their temperature is. So even things that are solid and don't feel cold to the touch, well, they do have a temperature, some temperature that you could take. And there is some movement happening with those molecules. It's very small movement, kind of like vibrations, but it's there. So what we're going to do real quick is just write down solids, liquids, and gases and kind of write down how the movement is happening. So with solids, atoms are packed together and they vibrate or wiggle around. With liquids, atoms can move around a bit more freely and they can bounce off of each other. And it's, I don't know, I like to think of that as almost like people swimming in a pool. They're kind of bound to the pool. They can't really get out of the pool unless they climb out. So if you have a lot of people in a pool, they're kind of bouncing off each other, but they're kind of contained to one spot. And lastly, we have gases, and that's almost like the bumper cars of the three states that we'll study. We have atoms moving quickly, bouncing off each other in every direction in kind of a very random way. So let's take a look really quickly at what solids, liquids, and gases look like at the atomic level. So here the solids are, and the solids you can see are kind of contained to one spot, but they are vibrating and wiggling around. And the warmer they are, the more wiggling happens. So that's a solid. Liquid, you can see that it's kind of like the pool analogy that I said a little bit earlier, that they're kind of bound to be in one spot, kind of near each other. Every once in a while, you'll see a few that kind of escape. And it's almost like a few that kind of get out of the pool and then jump back in. This is what happens when you pour a really hot cup of coffee. Some of the liquid molecules from the coffee can jump out. And when they jump out, they turn into a gas. So the ones that are jumping out, doesn't look like any are right now, but if we see one that kind of jumps out, they're going fast enough to actually jump into the gas stage. All of these liquid molecules look like they're behaving right now, though. And here's gas. Gas, there is the most movement. They're moving around very freely, and there's the most kinetic energy, the most movement. So gas would be the warmest of the three states. So we have solid, which is the coldest, the least amount of movement. Liquid, which is the middle amount of movement, and they're still kind of bound to one area, but they have a little bit more freedom, and sometimes they escape into the gas state. And gas, where they're moving around with the most kinetic energy, and there's the highest temperature. There comes the question, and that question is, what happens when the molecules stop moving, right? So the colder they get, the less movement happens. So is there some point where they don't move at all? The answer is yes, there is. It's called absolute zero. It's when atoms that are in a solid state stop vibrating. They don't move at all. They're totally stopped. Since they aren't moving at all, that means that they can't get any colder. Think about it. They can't move at all. How can they not move more? How could they slow down if they're not moving? So that means that there's some limit to how cold the universe can get. So that limit in Celsius is negative 273. In Fahrenheit, negative 459. And in Kelvin, that's what zero is. Kelvin is the K there, and that's more of a scientific scale. And you could probably see why scientists like Kelvin, because zero is as cold as it gets. There's no negative value in Kelvin. In Fahrenheit and Celsius, there are negative values, but Fahrenheit and Celsius have their own purpose. Celsius is good for looking at and studying water, because water freezes at 0 Celsius and boils at 100 Celsius. Fahrenheit is good for weather. 0 Fahrenheit is pretty darn cold. That's about as cold as it gets. And 100 is about as warm as it gets in Fahrenheit. So all three temperature scales have their own purpose. Let's talk next about energy. So it takes energy to make molecules move around. Think of it this way. It takes energy for you to move around, so it should also take energy for molecules to move around. The faster they go, the more energy it requires to move them. And also, we can think of it this way. If they're moving faster, that's a higher temperature. So it takes energy to make things to go higher to a higher temperature. And that's no surprise to anybody. If you want to heat something up, you have to have some sort of energy, whether that's a stove that's run on electric energy or gas energy, or even when you run around, some of your stored chemical energy in your body from the food you eat cause you to warm up. Heat is the what we call the energy that transfers from one thing to another. So if you want to warm something up, you need to put energy from one place to another. Heat is one way to transfer energy from one set of molecules to another to make them go faster and to warm up. This is a picture I really like. On the left, you have a leaky house. And I don't mean that the windows are open or anything like that. This is just a house without insulation. So what insulation does is it prevents those molecules that are moving very fast in your house that keep you warm in the winter. It prevents them from getting out of the house. That's what insulation does. If you don't have insulation, then the heat can escape your house. And in the winter time, when the molecules outside are moving very slowly, basically you're heating up the outside when you don't have insulation. So you're making the air molecules go faster outside from heating the heat from your house. When it's insulated, like on the right side, it's more comfortable because the heat, your furnace doesn't have to keep working all the time, and also saves money because it doesn't have to go work all the time. You keep the fast-moving molecules in your house and kind of make a barrier between the fast-moving molecules in your house and the cold, slow-moving molecules outside. In order to measure heat, we have an equation, and that's what we're going to work on the rest of this video. The equation is Q equals mc times delta T. Now, there's only 4 variables in this equation. Q, m, c, and delta T is 1 variable. Delta just means change in. We'll look at that a little closer in a second. Q is the amount of heat energy that you can add or remove to a substance, and the unit for heat energy is calories. So you've probably heard of calories before, but never thought of them as a unit or a measurement for energy. C is specific heat. What we'll see in a little bit is that certain substances like water and hydrogen, it takes a lot of energy to raise their temperature, while other things like glass, it's really easy to change their temperature. There's not a lot of energy you have to add. So every substance has a different specific heat. C is the variable for specific heat. M is the mass, which you've seen in the density equation before. And then delta T is how much the temperature has changed. I like to use this little mini equation to help me figure out delta T. Delta T, or the change in temperature, is the final temperature minus the initial temperature. So let's do 2 Q equals mc delta T problems. The first one is, how many calories of energy were absorbed into a sample of water, that's 3,000 grams sample of water, whose temperature went up from 24 to 28 degrees Celsius. And we know that the specific heat of water is equal to 1. All right, let's start with what we're given. We're given that the sample is a 3,000 gram sample. So that's the mass. We're also given that the temperature goes from 24 to 28. So we can figure out delta T. Delta T is the final temperature minus the initial temperature. So the final temperature was 28, the initial temperature was 24, so the change in temperature was 4. The last thing we're given is the specific heat. That's letter C. Specific heat for water is equal to 1. Unknowns. Well, we're looking for the amount of energy that was added. So, we're looking for Q, because Q stands for heat energy. E is our equation, which is Q is equal to MC times delta T. When we substitute in what we know that mass is 3,000, we know C is equal to 1.0, and we know delta T is equal to 4. So Q is equal to 3,000 times 1 times 4, that's 12,000. And the unit for heat is calories. We could just put cal down for that. And that's number 1. The second guess method that we'll do is a 4-gram sample of glass was heated from 50 to 90 degrees Celsius and was found to have absorbed 25.6 calories of energy to do so. What's this type of glass's specific heat? So what we'll look at real quick is you can see that there's a lot of different substances, and all those substances have a different specific heat. So we're using this type of specific heat, this unit of specific heat, and you can see that there are a number of values here. You see aluminum is pretty easy to heat up because it has a specific heat of 0.21, whereas something like, I don't know, helium is a little harder. It's actually a lot harder to heat up helium because it has a specific heat of 1. It takes a lot more energy to raise the temperature of helium than it does for aluminum. You might see that this website has 3 different kinds of glass, and each one has a different specific heat. So let's figure out what type of glass we're working with in this problem. We're given that we have a 4-gram sample. That's the mass. We're also given the temperature change, delta T, which is the final minus the initial temperature. The final temperature was 90, and the initial temperature was 40. So 90 minus 40 is 50. We also know how much energy was absorbed, so we know Q is equal to 25.6 calories. Next step is the unknown. We're looking for the specific heat. And if we can find the specific heat, we can find what type of glass it is. So specific heat is C. The equation is, Q is equal to MC times delta T. Let's put in what we know. Q is equal to 25.6. M is equal to 4. C we don't know, so I'll leave that for a second. Delta T is 50, and there's C right there. So to solve this one, what we can do is we can say 25.6 is equal to, let's see, 4 times 50 I know is 200. That's just 4 times 50 times C. So if 25.6 equals 200C, if I divide each side by 200, I get C is equal to 0.16. So that's our answer. Let's see what type of glass that is. Alright, so it looks like we're working with crown glass, which there's lots of different kinds of glass. Some glass shatters in different ways than others, and they all have different ways that their molecules are bonded together. So that's why we have different types of glass, and they heat up differently because their molecules are arranged differently and have different properties. And that's it. That's all about kinetic theory and heat.